Question 39 from the paper that was administered in February, March of 2018. Question paper 12 from ACE Physics Syllabus Code 9702 reads, a nucleus of neptunium-236 contains 93 protons and 143 neutrons. This nucleus decays with the emission of an alpha particle. The nucleus formed then emits a beta minus particle. Which diagram shows the changes in the number P of protons and the number N of neutrons in these nuclei? Okay, so I misspoke earlier when I said this is the nucleon number. This is not, this is the number of neutrons that they've plotted here. This is the number of protons that they've plotted here. Okay, so the nucleon number, remember, is all of the neutrons plus the protons. So here's just the neutron number, here's just the proton number. So if you emit first an alpha particle, or I guess maybe another way to solve this is to write the reaction out. So let's start with that. So we've got a neptunium-236 with 93 protons. All right, that's what we're starting out with. That's going to decay via alpha emission. Let me actually clear that. Do this. Neptunium-236, 93, decays via alpha emission. So that's a 4-2 helium nucleus. So that's the alpha particle. So that's, mathematically just the proton number is conserved, the nucleon number is conserved, and so this is going to go down by 4. So we're going to have 232. This is going to go down by 2, so that's 91, and that's what? Protactinium. So we got protactinium, and then as a separate reaction, that protactinium 23291 is going to undergo a beta minus decay. So remember what that is. That's a 0, -1 electron. So this number doesn't change. You still have 232 nucleons. But what number? -1 equals 91. So that's going to be 92, right? 92 minus 1 would be 91. So on the right side of this equation, the protactinium has increased its proton number, right? It's gone up by a proton. So this is an example of beta minus decay. That's a beta minus particle where a neutron transmutes to a proton, right? A down quark flips to an up quark. So think about it in terms of quarks. 92, that is uranium. So we end up with uranium-232, a isotope of uranium. Neptunium undergoes 2 reactions. And so you want to start out with how many neutrons. That's maybe the first thing that we could calculate is just what is 236, the total number of nucleons in our neptunium, minus the 93 that are positive. 6 minus 3 is 3. Can't subtract 3 from 9. Let me regroup over here. 13 minus 4, 143. So it should start out at 143, which is like that one does, that one does, that one does, and they all start at 143. So that doesn't help us, but at least gives us a good starting point. What's going to happen next? Well, the proton number goes down by 2. So we needed to kind of go from 93 here. See how they're all at 93 also? We need to go from 93 down to 91. So it's like it goes down to 91. This one is at 93. It goes down to 91. Okay. This one is at 93, but then it goes like up to 95. And so that'd be like if it absorbed an alpha particle or something, it would make it less stable. So that's no good. This one, 93, goes down to 91. So, by considering the first decay, you can eliminate this one as incorrect. Now we need to think about the next one. So if we first transmute, we go down from 143. I'm sorry, we consider the proton number, right? We went from 93 down to 91, okay? But did the neutrons also sort of get correct there? And so how many neutrons were in this protactinium? In other words, this first decay should give us the sort of data point of protactinium. We could do a very similar calculation we did over here. Just so anytime you have a nuclide symbol and you're interested in what's the number of neutrons, you just subtract the the protons from the nucleons, right? You can get that. So what's 23 minus 9? 14. You have 141, that would be the neutron number of this protactinium. So after this first transmutation, you want to be, 91, 141. So that one's good. 91, that one we can eliminate, right? It's down here at 139. Okay, so this one we can eliminate. Again, just using the first decay. That doesn't get it right. So it has to go down to 91 protons, but it's also got to be at 141 neutrons after that first decay. So this arrow represents the first decay. Is this one also correct? So it goes down to at 141. So right now it could be, either B or D, right? We've eliminated these two. We haven't even considered the second decay, this one over here, this beta minus, but it's very clear sort of, what's going to happen there. So just sort of being very careful and thinking through it, clearly understanding the reactions, and these ones, should be very forthcoming. So the protactinium, which agrees with this point, this is our protactinium, it's going to go up now to uranium. So it's increasing its proton number, okay? And so that means it's got to go up to 92. This one goes down to 90, okay? So this one goes up to 92, but wait, its nucleon number also drops there. Right, so it's from 141, it goes down to 140. Why is that the case? That shouldn't be the case. Right, because it's just a beta minus. Okay. The nucleus forms, then emits a beta minus particle. Oh, that's right. We're not looking at nucleon. We're looking at neutron. That should be. All right, so yeah, so because a neutron became a proton, right? So this one has to go down. So this 141, remember, this is the number of neutrons. So that is going to go down, right? The nucleon number stays the same, like the 232 still stays 232. But if we were to do the neutron calculations, right? So like one of these became a proton, so one less of these is a neutron now. So the neutron number in this uranium isotope would actually be 140, right? So we can see that choice D must be the correct answer.